Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking up at the night sky. You're just staring out into deep space.
Right. Just a completely clear, dark night.
Exactly. And suddenly you witness an explosion so unfathomably powerful, so overwhelmingly intense that it shines 10 or maybe even 100 times brighter than a standard supernova.
It's a scale of energy that's almost hard to wrap your head around.
It really is. I mean, we are talking about events that outshine their entire host galaxies. And not just for a day or two, but for months at a time.
Which completely breaks the standard models we have for stellar death.
Yes. You are looking at one of the universe's ultimate thermodynamic mysteries, and today we are stepping into a monumental breakthrough in astrophysics. We are exploring the very first confirmed observation of the birth of a magnetar.
It's an incredible milestone.
It really is. It's a discovery that finally solves a 16-year-old cosmic cold case. And in the process, it proves that Einstein's general relativity isn't just some elegant mathematical framework for describing gravity.
No, it is actively physically shaping the light curves of exploding stars.
Exactly. So our mission today is to unpack exactly what these bizarre cosmic engines are. We're going to analyze how a mathematically precise sort of chirp in the light of a galaxy a billion light years away cracked the case.
And examine why this fundamentally shifts our entire paradigm regarding the universe's most extreme fireworks.
Because the implications of this observation really they cannot be overstated.
They cannot. We are witnessing this incredibly rare moment where highly complex predictive theoretical physics seamlessly aligns with observational reality.
Which doesn't happen every day.
No, it doesn't. For years, astrophysicists have possessed the mathematical models detailing the energy budgets required to power these events. We understood the theoretical limits of stellar collapse.
The math was there on the whiteboard.
Exactly. But possessing a theoretical model of a central engine is a far cry from empirically capturing that engine in the act of altering its surrounding environment.
Right, actually seeing it happen.
To finally isolate the specific relativistic mechanics powering these blinding explosions, it not only validates decades of rigorous computational work, but it forces us to reevaluate the dynamical evolution of stellar death.
It takes it from theory to reality.
It transitions the Magnetar from a mathematical necessity to an observable mechanical reality.
Okay, so to truly appreciate the magnitude of this observation, you really have to understand the specific thermodynamic puzzle that emerged back in the early 2000s.
Right, with the discovery of superluminous supernova.
Exactly. Because anyone familiar with stellar evolution knows the standard core collapse model.
The textbook definition.
Right. A massive star, say something 25 times our sun, exhausts its nuclear fuel. The iron core collapses under its own gravity, and the resulting rebound drives a shockwave through the outer envelope,
creating a spectacular explosion.
Boom, supernova. Now, the energy budget for that standard event is relatively well understood, right? It relies heavily on the radioactive decay of elements like nickel-56.
Synthesizing the blast itself, yes.
And that decay powers the late-stage light curve. It's what keeps it glowing. But these superluminous events, they fundamentally broke that energy budget.
They absolutely shattered it.
Because they were outputting these sustained luminosities that simply could not be explained by the standard mass limits of radioactive decay. Let's unpack that a bit. Why couldn't it just be a really big normal supernova?
Well, the nickel-56 decay model works perfectly for a standard core collapse supernova because the diffusion of photons through the expanding ejecta matches the decay rate of those radioactive isotopes.
Okay.
But with superluminous supernovae, the sheer volume of photons being emitted, and over such an extended timescale, it created this glaring discrepancy.
Like the math just stopped working.
Completely. If you attempt to model the light curve of a superluminous event using only nickel-56, the required mass of the nickel alone often exceeds the total mass of the entire progenitor star.
Wow. So you'd need more nickel than the star even had stuff to begin with.
Exactly. It is a physical impossibility.
Yeah.
This meant that the kinetic energy of the initial shockwave and the subsequent radioactive decay were utterly insufficient to explain what we were seeing.
So something else had to be powering it.
Right. The expanding shell of stellar debris required a continuous, immense injection of fresh thermal energy.
A central engine.
Yes, an engine operating long after the initial collapse, just pumping energy in to maintain that extraordinary luminosity.
Which brings us to the theoretical framework proposed back in 2010. We had theorists Dan Kazin at UC Berkeley, Lars Bildston, and Stan Woosley at UC Santa Cruz.
Brilliant minds.
And they independently converged on this genuinely radical mechanism. They proposed that the necessary energy injection wasn't coming from radioactive decay at all.
Not even a little bit.
It was coming from the rotational kinetic energy of a newly formed magnetar. Now, okay, let's unpack this. To understand why this hypothesis was so compelling, we really need to look at the extreme parameters of what a magnetar actually is.
Especially in the immediate aftermath of a core collapse.
Right, because we aren't just talking about a highly magnetized neutron star here. We are talking about an object operating at the absolute extremes of physics.
That's right. When the iron core of a sufficiently massive star collapses into a neutron star, it conserves the angular momentum of the original stellar core.
Like an ice skater pulling their arms in.
A perfect analogy. Because the radius shrinks from thousands of kilometers down to roughly 10 kilometers, the rotation rate just skyrockets.
It spins up insanely fast.
And if the progenitor star possessed a strong initial magnetic field, or if convective dynamos during the collapse amplify that field, you generate a magnetar.
And the numbers here are just wild.
We are looking at surface magnetic fields on the order of 10 to the 14th or even 10 to the 15th Gauss.
Which, to put that in perspective for you listening, that is roughly a quadrillion times stronger than Earth's magnetic field.
It's almost unimaginable. And in its infancy, right after the collapse, this 10-kilometer-wide sphere can rotate with a spin period of just 1 or 2 milliseconds.
So wait, let me just make sure we're painting the right picture here. You have a mass greater than our sun.
Correct.
Compressed into the size of a small city.
Yes.
Spinning 1,000 times a second.
More than 1,000 sometimes.
And generating a magnetic field so intense it literally distorts the electron clouds of atoms.
It bends the very fabric of atomic structure, yes.
That is terrifying and amazing. So the Kazin, Bildston, and Woosley model hypothesize that this extreme object basically acts as a macroscopic particle accelerator.
Exactly. The rapidly spinning hyperstrong magnetic field generates an immense electric field.
Right.
And that accelerates charged particles to relativistic speeds, driving this continuous, incredibly powerful wind of high-energy radiation and electron-positron pairs.
And this is the mechanism known as spin-down luminosity, right?
That's the term, yes.
Yeah.
The magnetar is essentially braking. As it spins, it's transferring its massive rotational kinetic energy into the surrounding environment via magnetic dipole radiation.
So it's slowing down, but dumping all that energy into the debris around it.
Exactly. This relativistic wind slams into the inner boundary of the expanding supernova ejecta, and that generates a highly pressurized superheated bubble.
Okay, I can visualize that.
As the magnetar spins down over days and weeks, it continuously pumps thermal energy into the expanding debris. Now, because the ejecta is highly opaque, it has a very high optical depth, this injected energy cannot escape immediately.
It's trapped.
Right. It diffuses slowly, heating the outer layers and powering the brilliant, sustained light curve that defines a superluminous supernova.
And Dan Kazin elegantly referred to this entire mechanism as a theorist's magic trick.
Which is such an apt description.
It really is. That phrasing perfectly captures the frustration and the brilliance of the model, because the math checked out flawlessly.
It did. If you input a 1 millisecond spin period and a 10 to the 14th Gauss magnetic field into the equations, the resulting spin-down luminosity perfectly matches the light curves of superluminous supernovae.
It's a perfect fit, but the trick is that the central engine is entirely obscured.
Hidden behind the curtain.
Exactly. The magnetar is buried deep beneath light years of dense, optically thick stellar debris. You cannot observe the magnetar directly in the optical, X-ray, or gamma-ray spectrums because the ejecta just blocks everything.
It acts as an impenetrable wall.
Right, so you are only seeing the glowing exhaust. You are never seeing the engine itself.
And that's a huge problem for astronomy. The scientific method demands empirical verification. For over a decade, this was the central observational challenge in the field. How do you confirm the existence of an engine you fundamentally cannot see?
You can't just say, well, the math works, so let's call it a day.
No, you absolutely cannot. The theoretical community knew that if a magnetar was responsible, its energy deposition was making the debris superluminous. but there was no secondary signature.
No smoking gun.
Right. There's no independent variable that could definitively rule out other potential, albeit less likely, power sources. To confirm the Magnetar hypothesis, astronomers needed a highly specific dynamic signature in the light curve.
Something that could only be produced by the geometry and mechanics of a spinning, highly magnetized neutron star.
Precisely.
And that specific signature finally materialized. We fast forward to December 2024, shifting this from a theoretical exercise into an unprecedented global observation.
The discovery of SN 2024-05.
Yes, a supernova situated at a redshift that places it roughly 1 billion light-years from Earth.
A staggering distance.
And at that distance, capturing the high-resolution, high-cadence data required to analyze the subtle dynamics of a light curve, I mean, that is an engineering marvel in itself.
It truly is.
This observation relied heavily on the Las Cumbres Observatory, or LCO, which is this globally distributed network of 27 robotic telescopes.
And the architecture of the LCO network is absolutely critical to this discovery.
Tell us why.
Well, when studying transient astronomical events, the biggest enemies of data collection are daylight and weather.
Right. The sun comes up and you're done.
Exactly. A single observatory can only track an object for a fraction of a day, leading to significant gaps in the photometric data.
Yeah.
But by utilizing a network of robotic telescopes distributed across multiple longitudes, the LCO allows for continuous, unbroken observation.
Like a relay race.
Exactly like a relay. As the Earth rotates and the target dips below the horizon for a telescope in Hawaii, a telescope in Australia is already picking it up.
Wow.
And then it's followed by South Africa, and so on. This global relay enables astronomers to generate a pristine, high-cadence light curve, documenting the exact fluctuations in brightness without the typical diurnal interruptions.
It's just relentless observation, and this relentless observational capability was applied to SN 2024-05 for over 200 consecutive days.
A massive stakeout.
Basically, graduate student Joseph Farah at UC Santa Barbara, working with LCO astronomer Andy Howell, meticulously analyzed this massive data stream. Now, initially, the light curve behaved exactly as expected for a superluminous event.
It climbed in brightness, hitting its peak luminosity around 50 days post-explosion.
The energy output was staggering, entirely consistent with the Magnetar spin-down model. But the critical anomaly didn't appear during the peak.
No, it appeared during the fading phase, the decaying tail of the light curve.
Right. Normally, as the central engine spins down and the expanding ejecta cools, what happens?
Typically, the light curve should follow a relatively smooth, predictable, exponential decay. It just slowly fades out.
But the photometry for 2024-05 deviated violently from a smooth fade. The luminosity began to oscillate.
The brightness dropped, then spiked, then dropped again.
It generated this series of discrete bumps in the light curve. And this wasn't random noise or chaotic flickering from bad weather on Earth. The data revealed exactly 4 distinct high-amplitude bumps.
And what's fascinating here is the structural nature of those 4 bumps. That's where the data completely diverges from standard models.
Because they weren't evenly spaced.
Exactly. Farah noted that the temporal spacing between these peaks was not uniform. The period of the oscillations was gradually, precisely shortening.
So they were getting closer together.
Right. The time between the first and second bump was longer than the time between the second and third.
Which was longer than the time between the third and fourth.
Precisely. And Farah used the perfect analogy to visualize this data set. He compared it to a chirp.
I love that analogy. Let's break that down explicitly for everyone. If you look at the waveform of a bird's chirp or even a gravitational wave merger, the frequency of the oscillation increases as the event progresses.
The sound gets higher pitched because the waves are compressing temporally.
Exactly. And the light curve of this supernova was doing the exact same thing, accelerating its stroping effect as it faded.
And the presence of this specific accelerating periodicity immediately invalidated the leading alternative explanations for fluctuations in supernova light curves.
Because in previous observations, if a light curve exhibited maybe a singular bump or a minor fluctuation, what did astronomers usually blame it on?
They often attributed it to circumstellar interaction. The idea being that if the progenitor star underwent heavy mass loss episodes prior to collapsing, it would be surrounded by dense shells of gas.
Like blowing smoke rings before it dies.
Essentially, yes. And when the highly supersonic supernova shockwave impacts one of these circumstellar shells, the kinetic energy is converted into thermal radiation. That creates a temporary flare or bump in the observed light curve.
But the problem with the circumstellar interaction model here is that it's inherently stochastic.
It's chaotic.
Right. The mass loss history of a dying massive star is messy. The distribution of surrounding gas is highly irregular. You might get one collision or perhaps a couple spaced out completely randomly depending on where the clumps of gas just happen to be.
Exactly. But you absolutely do not get 4 massive, mathematically organized collisions that perfectly accelerate in frequency.
It's just too clean.
Way too clean. The precise periodicity of the chirp fundamentally requires a rotating, dynamic mechanical system operating from the inside out, not a random series of external collisions.
Okay, so this realization forced Farah and his team to construct a totally novel mechanical model, one capable of producing an accelerating strobing light effect from deep within the opaque ejecta.
And they turned to the dynamics of fallback accretion.
Let's talk about fallback accretion, because when a core collapse explosion occurs, not all of the stellar material achieves escape velocity, right?
Right. A significant fraction of the inner envelope, lacking the kinetic energy to overcome the immense gravity of the newly formed neutron star, just stalls. And then it falls back inward.
It rains back down on the core.
Precisely. But due to the conservation of angular momentum from the original star's rotation, this falling material cannot drop straight down onto the neutron star's surface.
It can't just plunge in.
No, instead it spirals inward, flattening into a dense superheated accretion disk.
And this is where the geometric complexities of the explosion become paramount, because a supernova is not a perfectly spherical, highly symmetrical event. It's not this neat little drawing in a textbook.
Not at all. The core collapse and the subsequent neutrino-driven convection are wildly turbulent. Neutron stars often receive massive kicks during formation.
Kicks?
Yes. Asymmetrical forces during the explosion can literally kick the neutron star, accelerating it to hundreds of kilometers per second in a specific direction.
Wow.
And because of this inherent chaos and asymmetry, the angular momentum vector of the fallback material is almost never perfectly aligned with the spin axis of the central magnetar.
Which creates a profound misalignment.
A huge one.
You have a central magnetar spinning on one axis, right? Surrounded by a massive, superheated accretion disk rotating on an entirely different tilted axis.
It's a wildly unstable geometric configuration.
And this configuration, a misaligned disk orbiting a rapidly rotating ultra-compact mass, is the precise environment where things get truly weird. This is where the most extreme predictions of Albert Einstein's general relativity step in and become dominant.
Specifically, we have to look at the dynamics governed by the Kerr metric.
The Kerr metric?
Yes. Which describes the geometry of empty spacetime around a rotating, uncharged, axially symmetric black hole, or in this case, a rapidly rotating neutron star.
Okay, so Einstein's general relativity dictates something called frame dragging, or Lense Thirring Precession.
That's the punchline, yes.
Let's break this down, because in a classical Newtonian framework, gravity is simply a force acting across a distance, like an invisible tether.
Right. Newton sees space as a static stage.
But in general relativity, gravity is the curvature of space-time itself. So when you have an object as dense as a magnetar spinning at incredibly high velocities, it doesn't just sit in a static depression in space-time.
Not at all. The mass and the extreme angular momentum of the magnetar literally grab the fabric of space-time itself and drag it along in the direction of the rotation.
Like spinning a bowling ball in a vat of honey.
That's a great visual. Space and time are physically twisted around the central engine.
And because space-time is being dragged, it exerts a profound mechanical force on anything orbiting within it.
Yes, and remember our misaligned accretion disk.
It's sitting directly within this heavily twisted region of space-time.
Exactly. Because the disk's orbital plane is tilted relative to the magnetar's equatorial plane, the frame dragging effect applies a differential torque across the disk.
It's twisting the disk.
It is. This torque forces the entire accretion disk to precess. So instead of spinning smoothly like a stationary record, the entire plane of the disk wobbles around the magnetar's spin axis.
Like a gyroscope.
Or a spinning top that's starting to lose momentum. It wobbles. And because the inner regions of the disk are tightly coupled together magnetically and frictionally, the disk tends to precess as a single, rigid, solid body.
So you've got this tilted disk wobbling as one solid piece. And the solid body precession of the misaligned disk provides the exact mechanism needed to create the anomalous light curve.
It's the lighthouse effect.
Yes. Let's visualize the mechanics here. We have the central magnetar pumping out immense spin-down luminosity, thermalizing the inner region of the ejecta. It's brilliantly bright.
But surrounding that central light source is this thick, opaque, tilted accretion disk.
Right. And as the disk precesses, as it wobbles, Driven by the dragging of space-time, its orientation relative to our line of sight constantly changes.
It functions precisely like a cosmic lighthouse, but functioning through obscuration rather than directed emission.
Meaning it blocks the light instead of shining a beam.
Exactly. When the precessing disk's raised, thicker edge wobbles into our line of sight. It heavily obscures the brilliant thermal radiation from the central engine.
Which causes a sharp dip in the observed brightness.
Right. And then, as the disk continues its precession and that thick edge rotates out of our view, we are granted a clearer, less obstructed view of the central engine's emission.
Resulting in a spike or a bump in the light curve?
The entire inner geometry of the supernova is basically acting as a massive strobing shutter.
That perfectly explains the periodic bumps. But the real genius of this model, the aha moment, lies in how it seamlessly explains the chirp, the accelerating frequency of those bumps.
Because the accretion disk is not a static structure.
Right, it is dynamically evolving. As the material in the disk interacts through internal friction and magnetic viscosity, it continuously loses orbital energy and angular momentum.
This viscous dissipation causes the material to slowly spiral inward. It's accreting onto the magnetar.
And as it loses energy and slides inward, the effective radius decreases. It shrinks tighter and tighter around the magnetar.
And this is where the math locks in perfectly. The frequency of Lense Thirring Precession is highly dependent on the radius. Specifically, the precession frequency is proportional to the inverse cube of the radius.
So smaller radius means much, much faster wobble.
Exponentially faster. Therefore, as the viscous timescale drives the disk inward, placing it deeper into the gravitational well and deeper into the most intensely dragged regions of space-time, the rate of precession dramatically accelerates.
The disk shrinks, the wobble speeds up, and the strobing effect of the obscured light flashes faster and faster.
It's beautiful.
The gradual shortening of the time between the observed bumps in the light curve is the direct, observable manifestation of a shrinking accretion disk being dragged by the twisting of spacetime.
The mechanics are just so exquisitely intertwined.
And Farah and his team made it a point to emphasize that this marks an unprecedented milestone in astrophysics. This is the very first time that the equations of general relativity have been absolutely required to model and explain the macroscopic light curve of a supernova.
Which is a paradigm shift. We frequently rely on general relativity for modeling black hole event horizons or cosmological gravitational lensing, but utilizing the Kerr metric to map the mechanical thermal output of an exploding star.
That is entirely novel territory.
Completely. And the rigor applied by Farah's team to ensure this was the only viable explanation is highly commendable. In astrophysics, invoking general relativity to explain a light curve anomaly is generally a measure of last resort.
Right, you don't jump to Einstein unless you have to.
Exactly. You must definitively rule out all classical mechanics first. And they did. They exhaustively modeled the system using purely Newtonian parameters.
Trying to find an easier answer.
They attempted to drive the precession via the classical quadrupole moment of the neutron star.
Which is just the fact that a spinning star bulges slightly at the equator, right? Creating an uneven gravitational field.
Correct. But the Newtonian timescale didn't fit the rapid evolution of the chirp. It was too slow.
They also explored magnetically driven precession too, didn't they? Looking at whether the intense magnetic field of the magnetar interacting with the plasma of the disk could induce the wobble.
Precisely. They modeled magnetic torques. But the temporal evolution of magnetic precession scales differently with the radius of the disk compared to Lense Thirring Precession.
So it wouldn't accelerate the same way.
Right. When they cross-referenced the mathematical predictions of magnetic torques against the observational data of the four bumps, the curves diverged. It just didn't match.
The puzzle pieces didn't fit.
It was only when they applied the strict relativistic equations for frame dragging that the theoretical model perfectly overlaid the empirical data from LCO.
The timing, the acceleration, the amplitude.
Everything locked into place. Andy Howell, the senior scientist at LCO, characterized it as an incredibly elegant explanation, taking the best-tested theory of gravity we possess and utilizing it to decode a completely opaque, chaotic system.
It's just brilliant. And this is where the capability to extract hard, quantitative data from a seemingly simple light curve becomes truly staggering.
The numbers they pulled out are amazing.
I am geeking out over these numbers. Because they isolated Lense Thirring Precession as the exclusive mechanism driving the chirp, they could literally reverse engineer the equations.
Right, because the rate of frame dragging is directly dictated by the angular momentum of the central mass.
So by carefully measuring the precise timing of the 4 bumps over that 200-day period, the astronomers were able to calculate the unseen engine's exact physical parameter.
Through all that noise and across an immense distance.
1 billion light years. They calculated the newly formed neutron star's spin period to be exactly 4.2 milliseconds.
Which is just a breathtaking velocity.
Yeah.
A 4.2 millisecond spin period means this stellar remnant is completing nearly 240 full rotations every single second.
240 times a second for something the size of a city, but heavier than the sun.
It defies everyday intuition. And furthermore, by analyzing the total energy budget required to power the peak luminosity, and correlating it with the spin-down rate inferred from the disk's evolution, they could constrain the magnetic field strength.
And what did they find?
The data yielded a surface magnetic field of approximately 3 times 10 to the 14th Gauss, or roughly 300 trillion times the magnetic field of Earth.
300 trillion times. These specific parameters are not just interesting trivia, they are the absolute, undisputed theoretical hallmarks of a newly born magnetar.
Yes. The numbers perfectly align with the predictions made by Kazin, Bilston, and Woosley 16 years prior.
It's the ultimate validation. We didn't just find a weirdly bright supernova. We extracted the rotational velocity and the magnetic field strength of an object we cannot even directly see.
Located 1 billion light years away.
By measuring how it warped space-time.
It's a triumph of observation and theory.
It really is. This is exactly why Alex Filippenko, the distinguished astronomy professor at UC Berkeley, hailed this observation as the definitive evidence the field have been waiting for.
Because the 2010 model only assumed the magnetar was there. It was operating as a black box injecting energy.
But Farah's paper essentially shattered the black box. They pulled back the curtain. The intricate dynamic interaction between the magnetar, the space-time metric, and the accretion disk projected the engine's shadow right onto the supernova's light curve.
The magic trick is real.
The magic trick is real. It is a phenomenal synthesis of theory and observation. It definitively confirms that the core collapse of a massive star can indeed produce these hypermagnetic millisecond pulsars.
And that the spin-down luminosity of these engines is the direct mechanical cause of the superluminous phenomena.
But, and this is important, we have to talk about the bigger picture and the caveats, because we need to apply the brakes gently here.
Right. It is crucial that we maintain scientific rigor.
We can't avoid over-extrapolating from a single, albeit groundbreaking, data point. Does this mean all superluminous supernovae are magnetars?
No. And Filippenko correctly cautioned the community against adopting a monolithic view. We cannot immediately jump to the conclusion that every single superluminous supernova observed over the past 2 decades is powered by a magnetar.
The universe is rarely uniform in its extreme mechanics, so if we confirm the magnetar engine for this specific event, which we have, what alternative mechanisms remain viable for other supernovae, ones that perhaps lack this distinct lens-thirring chirp?
Well, the circumstellar interaction model we discussed earlier remains a highly viable explanation for a distinct subset of superluminous events.
The shockwave hitting clumps of gas.
Exactly. If a progenitor star undergoes an extreme episodic mass loss phase, perhaps shedding multiple solar masses of material in the centuries immediately preceding core collapse, the resulting shockwave interaction can absolutely generate sustained luminosities that mimic a magnetar-driven event.
But the difference would be in the details.
Right. The difference lies in the spectral signatures and the lack of precise accelerating periodicity in the light curve. You wouldn't see the perfect chirp.
Got it. And furthermore, Dan Kazin himself has continuously refined his theoretical models over the years, exploring the parameter space beyond just neutron star formation. He proposed a fascinating alternative.
The collapsor or black hole fallback model.
Yes. Let's talk about that.
If the initial massive star is exceptionally massive, or if the initial explosion lacks the energy to completely unbind the stellar envelope, the fallback accretion can exceed the Tolman-Oppenheimer-Volkoff limit.
Which is the maximum mass a neutron star can support before gravity overcomes neutron degeneracy pressure, right?
Correct. Gravity wins. In this scenario, the newly formed neutron star rapidly collapses into a stellar mass black hole.
And the black hole fallback model is incredibly compelling because it can also produce a superluminous event.
It can. The immense gravitational potential energy released by solar masses of material accreting onto a newly formed black hole can drive powerful relativistic jets and massive outflows,
which heats up the surrounding ejecta,
resulting in a highly luminous, sustained optical display. And crucially, a newly formed black hole can also possess a misaligned accretion disk.
Oh, wow. So we could theoretically observe Lense Thirring Precession and a similar chirping light curve from a black hole engine, too.
Exactly, which raises a fascinating diagnostic challenge for the future.
Because if both a magnetar and a black hole can possess a precessing accretion disk, how are astronomers going to distinguish between the two central engines in future observations?
It will require extremely precise analysis of the timescale and the energetics of the chirp. A magnetar has a solid surface and a rigid magnetic field.
Right.
This leads to different viscous dissipation timescales and disk coupling dynamics compared to the event horizon of a black hole. Furthermore, the total energy available from magnetar spin-down is capped by its maximum rotational velocity.
It has a speed limit.
Yes, whereas black hole accretion can theoretically tap into a much larger reservoir of gravitational potential energy.
So by meticulously analyzing the rate of the chirp's acceleration and correlating it with the total integrated luminosity of the supernova, future models should be able to differentiate the mass and the nature of the central compact object.
Mystery has evolved from a question of what is the power source to a highly nuanced demographic study of stellar death.
We now have confirmed proof of the magnetar mechanism, but the next phase of astrophysics really must determine the exact statistical distribution.
Right. What percentage of superluminous supernovae are driven by magnetars? What percentage are collapsers forming black holes? And what percentage are simply extreme examples of circumstellar collision?
And Filipenko noted that while the exact demographic fractions remain unknown, the sheer elegance and the definitive nature of the data from SN 2024 AFAV strongly suggests that the magnetar mechanism accounts for a highly significant portion of these events.
We have successfully transitioned a massive unknown variable into a confirmed, observable physical mechanism. And the timing of this theoretical confirmation perfectly coincides with a massive leap forward in our observational infrastructure.
Let's talk about what's next. Because the future of this specific branch of astrophysics is incredibly bright, largely due to the imminent operational start of the Vera C. Rubin Observatory in Chile.
It's going to change everything.
The Legacy Survey of Space and Time, or LSST, being conducted by the Rubin Observatory, is preparing to come online for the most comprehensive survey of the night sky ever.
It will fundamentally alter how we monitor the transient universe.
We are talking about an 8.4-meter telescope equipped with a 3,200 megapixel camera.
Just staggering specs.
Possessing a field of view so massive, it can photograph the entire visible southern sky every few nights. The volume of photometric data, the sheer density of the alert stream, is going to be unlike anything the astronomical community has ever processed.
The Rubin Observatory represents a paradigm shift from targeted observation to high-cadence, wide-field statistical surveying. Farah and his colleagues anticipate that the LSST alert stream will completely revolutionize our detection rates.
They won't have to rely on serendipitous targeting by the LCO network anymore.
No. Instead, the Rubin Observatory will systematically catalog the light curves of millions of transients. Farah expects that within the first few years of operation, they will identify not just one or two, but dozens, perhaps hundreds, of these chirping superluminous supernovae.
Finding dozens of these events means dozens of opportunities to extract the spin periods and magnetic fields of newly born magnetars.
It provides dozens of independent test beds for general relativity in the most extreme gravitational environments in the universe.
It moves the study of Lense Thirring Precession in supernovae from a singular anomaly to a robust statistical science.
It's an incredibly exciting time to be an astronomer.
It truly is. And when you look at the sheer scale of the physics involved, the twisting of space-time, magnetic fields in the hundreds of trillions of Gauss, the explosive death of stars, it is really easy to lose the human element.
It is.
But Joseph Farah provided a quote regarding his work on this observation that deeply grounds the science. He stated, "This is the most exciting thing I have ever had the privilege to be a part of. This is the science I dreamed of as a kid."
And that sentiment perfectly captures the fundamental drive of scientific inquiry. We build these incredibly complex theoretical frameworks, and we engineer these massive robotic telescope networks, not merely to catalog data, but to probe the boundaries of our understanding.
Right.
The initial mystery of the superluminous energy budget, the unexpected detection of the four bumps, the realization that space-time dragging was the only solution. These moments represent the universe pushing back against our current models.
As Farah insightfully noted, anomalies like the chirp are the universe telling us out loud and in our face that we don't fully understand it yet and challenging us to explain it. It is the ultimate intellectual gauntlet. So let's look back at the immense scope of the incredible journey you've just been on today.
It's been quite a ride.
We began with a seemingly impossible thermodynamic puzzle. A persistent, glaring luminosity a billion light years away that completely shattered the standard models of radioactive decay.
We trace that excess energy back to the 16-year-old theoretical predictions of Kazin, Bilston, and Woosley.
A hidden, city-sized magnetar spinning 1,000 times a second. And ultimately, through the rigorous analysis of a subtle accelerating oscillation in the fading light, we arrive at a wobbling, superheated accretion disk.
Physically forced into solid body precession by the relativistic twisting of space-time itself.
It is the definitive proof of Einstein's Kerr metric operating directly in the heart of an exploding star, proving Einstein right yet again.
It serves as a profound demonstration of the deep interconnectedness of physical laws.
It really does.
The macro-scale observation of a supernova's light curve across a billion light-years of space is ultimately governed by the micro-scale quantum state of neutron degeneracy pressure and the geometric warping of local space-time. It illustrates that the universe operates on a unified mechanical framework, regardless of the extreme scales involved.
And that is precisely why this specific discovery matters so much. It's not just abstract math. It is a testament to humanity's capacity to decode the invisible mechanics of the cosmos.
We are sitting on this small, rocky planet, utilizing mathematics and networked optics to reverse engineer the exact rotational velocity and magnetic field of an invisible stellar core.
Based entirely on how it distorts the space around it. We are effectively reading the physical fingerprints of gravity embedded in the decaying light of a dead star.
It's poetry, honestly.
It is. And as we conclude our analysis of this incredible event, we want to leave you with one final, lingering question to mull over.
Right. Think about this the next time you look up at the night sky. The definitive proof of this massive, hypermagnetic engine was hidden entirely within the subtle accelerating rhythm of a fading light.
If the precise, quickening chirp of a wobbling accretion disk was all it took to finally pull back the curtain and reveal a magnetar hiding inside a supernova,
what other bizarre, extreme, and currently invisible cosmic monsters might be actively hiding behind the blinding light of the stars you see in the night sky right now, simply waiting for us to develop the correct mathematical tools to finally listen to their unique rhythms?